I sometimes start that at the beginning, when she's
Huh?
so.
The best part of the videos is you, Marilla.
When you taking my test yesterday, you were just screaming to the speakers.
What speaker?
When he was editing the video.
Oh.
Wait, did you hear about fish yesterday?
Thank you, dear.
From these kids.
Did you hear? Oh, Jack, did you watch
Okay.
the video yesterday? Did you hear us say good luck picking up your foster children?
I just got that video sent to me.
Oh.
Conversations you hear from like this class in that video, just from those four, or something.
Yeah, I wish I could just like have my just like
You get a mic.
yeah, but then it takes away from the ambiance.
It takes away from our conversations.
Yeah. Okay, so if you want to order any of the solar merch, okay, I don't necessarily need the money today, but if you have that form, then just put that up into the tray, so I can get an idea of the order, and that's going to determine some other things. So, if you're still undecided, I would still take orders on Monday, because I'm trying to sort that whole deal out. But certainly if you have that, go ahead and put that up there, because that way I'll know kind of how to begin to plan some
I don't know if I want to.
She said you could do it on Monday, dude.
I know I spend too much money. But it's okay.
Yeah, we got it.
Background. Purpose.
Okay.
Yeah, also guys, get on top of it for the donating.
We'll get there. Let's see where we are after the merch in the book and all that good stuff.
Hey,
You have until Christmas, so.
Come until Christmas. Christmas?
Okay. So here's what we have left. So today we have angular motion. Monday we have angular momentum.
Yes.
Tuesday we review. Wednesday's a test. And then Thursday we start work. Literally we start work. And then Friday is Africa Day. So that's kind of the sequence of where we're at. Okay, so when you look at angular motion, so let's say, for example, I happen to have a wheel, which I do. And when you try to describe this motion, you have to deal with a couple of different scenarios. So you can have motion, okay, without it going anywhere. But you can also have motion and you have linear motion as well. So we have to be able to deal with both situations, okay? When something just spins in place versus something spinning and it's moving. So one of the key things that you have to begin to understand is this concept of radians. So when we talk about this wheel spinning, we have to be able to describe this motion, but we can't talk about meters because it really isn't going anywhere. So one of the key things that you have to get is that when you talk about angular motion, that's the idea of one revolution is 2 pi radians. Okay? So radians are this weird deal, because radians are what's known as a dimensionless number. So I'm never going to say, oh, it went 2 pi radian meters, or 2 pi radians meters per second, okay? So if it's 2 pi radians, that's it, okay? It's 2 pi radians, it's 2 pi radians. So the other thing that happens when you deal with angular motion is that basically the good variables are already taken up, okay? Distance was already taken with the d, and v was taken for velocity, and a was taken for acceleration. So the angular motion physicists, well, what's left? And they said, well, let's go Greek. Okay, maybe they were in a fraternity. I don't know. Let's use the Greek alphabet. Okay. So you're going to have 3 variables when you talk about angular motion. So if you're a little rusty on your Greek letters, so you have theta, omega, and alpha. And these are lowercase, just like you have like uppercase and lowercase. In our alphabet, you have uppercase and lowercase letters in the Greek alphabet. These are all lowercase. So this is omega, and this is alpha. So just to point this out, because if I don't, someone's gonna think they're clever and you'll think the first person in the history of humankind to make this observation. That looks like a butt, okay? So don't think you're clever. You go, Mr. Brookhaven, that looks like a butt. And you think you're the first person to ever notice that. You're not, okay? It's not funny. It does, okay? It is, but that's not the point. And so this is sometimes just called fish, okay? So a lot of times we're talking about theta butt fish, okay? So that's the story. The Greeks are spinning in their ways like, oh my God, what are you doing to our alphabet? Calling it butt. It's like, it's funny. Go with okay. So, by the way, I'm kind of losing my voice, so bear with me. So, but there's a similar type deal in the sense that if you talk about distance, right? Well, that's shown by the letter D, and that's measured in meters, okay? So if I talk about how far this remote control pushes, oh, what's the distance? All right, so many number of meters. So if you're talking about angular motion like this, we're going to talk about how many radians it moves through. So distance, the letter D, is equivalent to theta measured in radians. So if you keep your eye on this little piece of tape right here, as that piece of tape goes from here all the way back to that point, that made 1 revolution, okay? That traveled through 2 pi radians. Now, one of the things you'll see is that sometimes the radius of the object is part of the story, and sometimes it isn't. So if you look at, here's the sun, here's the earth. Earth makes 1 revolution around the sun. How many radians does it move through? 2 pi. Okay? Moon orbits around the earth. 1 revolution, 2 pi radians. Okay? Earth, or our sun, is getting drugged around the center of the Milky Way galaxy. Travels through 2 pi radians. Okay? So any circle, regardless of the radius, if it makes 1 revolution, that travels through 2 pi radians, okay? You're made up of billions and billions upon billions of little electrons that are moving around the nucleus of your atoms. They're traveling through 2 pi radians, okay? So one of the things you'll see is that this idea that 1 revolution is 2 pi radians is not dependent upon the size of the object, okay? 1 revolution is 2 pi radians regardless of the size, okay? Now, just like velocity is distance divided by time, that's the simplest way to do that. Oh, what's your rate function? So many meters per second. Oh, you're going to go out and you're going to drive down the road. Oh, you're driving at 20 meters per second. It's rate function. You are traveling a linear distance of 20 meters per second. So the same thing is going to be true of omega. So the simplest way to calculate that is theta divided by time. So if you look at this, that's going to be so many radians, maybe 1 revolution, divided by 2 seconds, whatever, okay? So this is oddly enough measured in radians per second, okay? Same idea. But now, just like this, what's the only time you can take distance and divide it by time to get velocity? It's the only situation you can do that. If you have constant velocity. The same thing is true here. The only time I can take radians and divide it by time to get my angular velocity is if it's constant. So if the wheel is speeding up, slowing down, something like that, I can't do that. But if I'm looking like, for example, the second hand on a clock as it goes around, hey, that's moving at a constant velocity. I can take radians and divide it by time. The Earth, as it goes around the sun, pretty constant velocity, I can do that. But if I take this wheel and I get it spinning, okay, and then I begin to slow it down, and I want to know how many, what's its velocity, I can't take radians and divide it by time in that situation because of the fact that it's slowing down. So the same rules apply. Even if you look at Newton's laws of motion, oh, okay, here's a wheel. Guess what? It's not going to begin to spin on its own until I apply a force to it. Then, guess what? Now it's gonna keep spinning until what? Until I apply an outside force to it, okay? So it's a lot of the same rules. If I apply just a little bit of force, I get just a little bit of acceleration. If I apply a bigger force, I get a bigger acceleration, okay? So if I want to slow it down slowly, I apply a little force. If I grab it, okay, apply more force, it slows down faster, okay? So it's a lot of the same ideas, we're just repackaging it. Then, just like linear acceleration is change in velocity over time, fish is change in angular velocity over time, okay? So just like you have v minus v naught over time as acceleration, guess what? And this is just kind of fun to say, you have but minus but naught over time, okay? Gives you fish. So but minus but naught over time gets you fish, which sounds weird unless you're in a physics classroom and go, oh, you're talking about angular acceleration. We get it, it's cool. Okay. Now, because we have to be able to deal with both situations, and this is on your equation sheet, don't memorize these, but there's 3 equations that allow us to go from linear motion to angular motion. And it's d equals r theta, b equals r butt, a equals r fish, okay? Now, what do you notice that all of those are dependent upon? All depending upon radius, okay? They are all dependent upon radius. So what this says is if you know how many radians it moves through and you know the radius, you can figure out how far that wheel is going to travel. If you know how fast you're spinning, that will tell you what the linear velocity is. How fast is it moving in meters per second? If you know the angular acceleration, you can figure out, oh, what's going to be the linear acceleration of that object, okay? So all of this allows you to do is cross this bridge. Now, for now, sucks losing your voice. Pretend that none of this exists. You have, what we just talked about is dead to you. It never happened, okay? That discussion has never taken place. Here's a bicycle wheel. It has a radius of 0.25 meters, okay? So here's this piece of tape. I'm going to put that down here at the bottom, okay, like this. And I'm going to have this bicycle wheel roll until that piece of tape gets back down to the bottom, okay? So I'm here. I'm going to roll this thing along until that gets back to that point. So what I want to know is how far did this bicycle travel in the linear distance as this piece of tape made 1 revolution? What?
2 pi.
Huh?
2 pi.
2 pi what?
Radian.
That's how many radians it moved through. You have half of it.
Is it circumference?
Oh, the circumference, okay, which is going to combine what you just said, okay? Now, how do you calculate the circumference of a tire?
Pie delicious. I mean,
Cherry pie delicious.
2 pi.
How about 2
2
pi
pi r.
Right, so this is where your 2 pi comes in, okay? So visualize this. Here's the other way some people like to look at this. Imagine that I take a piece of string and I wrap it all the way around the wheel. And then I lay that piece of string out. That's how far the wheel would travel as it went along. So, if the radius is 0.25, so I'll take 2 pi times 0.25 meters. Okay? Now, the math people will tell you, and I'm a recovering math nerd, okay? That was actually what I studied most in college. But I figured teaching math was just really boring. So I could speak the language. So they're going to say, oh, that's 2 pi times 1/4. Oh, that reduces to pi over 2. And you sound very scientific. Oh, it's traveling pi over 2 meters. Here's the problem, okay? Meter sticks don't measure in units of pi. What do they measure in? They measure in decimals, okay? So the math people will say, oh, that's never precise because it's pi over 2, right? They're right, okay? The problem is I can't measure pi over 2. okay? I don't have a meter stick that measures in units of pi. I have a meter stick that measures in decimals. So when you're doing this as a physics problem, do the math, like get this as a decimal. Somebody take pi and divide it by 2 and let me know what you get.
Why would it be?
1.57.
1.57? 1.57 meters, okay? Now that's something I can measure with a tape measure, okay? I can measure off 1.57 meters. So that means is if this wheel starts here and it goes around like this, it's gonna travel 1.57 meters. Cool. Okay. Now you're going, okay, great, Burkamp. So why'd you teach us those first equations? Here's the reason why. So now let's venture back up to this equation. Okay? Let's see if this one works. Okay, D equals R theta. So when that bicycle tire went through 1 revolution, how many radians did it move through? 2 pi. Oh. So that's going to be the radius of 0.25 meters times 2 pi, and oddly enough, that looks like 2 pi r. Okay, just reverse the sequence, which oddly enough, you're still going to get 1.57 meters. Okay?
So like the 2 pi is based off of a 1 meter radius, right?
Well, the 2 pi is just based upon off 1 revolution.
I mean the 2 pi. Yeah, the 2 pi. But like, you know.
The 2 pi or not the 2 pi?
I think it's based off
Are we 2
the
pi
circumference.
No, the distance, like if it was 2 pi times 1 meter, it would just be 2 pi radians. You know what I mean? So it's just like a proportion.
Yes, we'll get to that.
Oh, really? It comes more?
Oh, there's
more?
There always is. Now, here's an interesting idea. Let's say I take this 1 kilogram mass, and I have it roll 1 revolution versus having the bicycle tire roll 1 revolution. What do they have in common? If this rolls 1 revolution, and that rolls through 1 revolution. Same number of radians, right? If this moves through, if this rolls
Toby
1
Jackson to the
revolution,
front office, please.
That was sus. She pushed the wrong button.
yeah. Okay. So here's the deal. This rolls 1 revolution. The bicycle tire rolls 1 revolution. Do they move through the same number of radians?
Yeah.
Yes. But do they travel the same linear distance?
No.
No. Clearly, which one travels greater?
The bigger one.
Bicycle does, because it has a
Bigger
bigger
radius.
radius. Okay?
Wow.
Now, let's talk about this. So, if I take the 1 kilogram mass, and it has a radius of, say, I don't know, 0.05 meters, 5 centimeters, about like yay, okay? So if it rolls through 1 revolution, I'm going to go, okay, D equals R theta. So now I'm going to take 0.05 meters times 2 pi radians, and now what do you get? 0.314 meters. So here's what I want you to see that's in common. And sometimes radius is a factor and sometimes radius isn't. So if all I'm talking about is how far it goes, okay, linear distance, I have to know 2 things. I have to know how many radians it moves through, and I have to know the radius. But if I'm just talking about an object spinning, if this makes 1 revolution, if the bicycle tire makes 1 revolution, if the Earth makes 1 spin on its axis, all of that is still just 2 pi radians. Radius becomes a factor when you talk about the linear distance that it moves. Now, here's the odd thing. D equals R theta is a linear function. You go, it's not a linear function. Sure it is. Let me show you. So we can draw a graph, and we're going to put linear distance traveled on one side, and we're going to put theta down here, okay? So the first situation, we traveled through 2 pi radians, 1 revolution, right? So the bicycle tire, when it traveled through 2 pi radians, we said it traveled 1.57 meters, okay? So we have 2 points. We have 1.57 meters as my y coordinate, and we have 2 pi as my x component, right? That's my coordinates, 2 pi, 1.57. The other points are 0, 0. So out of random curiosity, let's find the slope of this line. So somebody take, change in y over change in x. So somebody take 1.57 meters, divide that by 2 pi. Now be careful when you're dividing by 2 pi, and you'll do this a lot. You have to put the 2 pi in brackets, otherwise what your calculator does is it divides by 2 and then multiplies by pi, okay? So if you're going to divide by 2 pi, you have to put that in brackets. So what do you get?
0.250.
Oh, oddly enough, you get 0.25 meters. How cool is that? What does that represent?
The radius?
Radius.
Oh, it's a linear function. The
Nice.
slope represents the
Oh, like y equals mx.
yes.
Yes.
Oh,
And
it's
x?
linear.
M is the
Slope, which is the radius.
the radius. Oh.
Theta is your x value, distance is your y value.
Y.
It's a linear function.
Oh,
Okay.
yeah.
Nice.
It's here for the math nerds. Yeah, give that up. Okay, now, interesting thing happens. What would that graph look like for the 1 kilogram mass?
The
Would it be more
same-
steep, less steep, or the exact same slope?
Less steep.
Why?
Less radius.
Yeah.
So for each revolution, it would travel
Less
smaller distance. So we said that would travel 0.314. So if we drew that line for this, it would be way down here at 0.314, okay? What about the Earth as it spins on its axis? So as the Earth
It'd be
spins on its
very-
axis, what would happen?
Wouldn't it be really big?
Large slope.
It'd be really, really big. Why?
Because the radius of the Earth's
Much
really
bigger.
big.
Yeah, 24 hours ago, and here we are 24 hours later, we've traveled through 2 pi radians. Earth is, we kind of got a big rock that's spinning, right? We would have traveled, imagine if we could take the Earth and make it roll along the surface, we would travel a great distance. So the Earth spinning would be this really, 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 really steep line because it would have a really, really, really big radius, okay? So here's what I want you to understand, okay? Listen to me, listen to me, listen to me, listen to me. When something makes one revolution, the only factor that influences that is the fact that one revolution is 2 pi radians. Whether it's an electron going around the nucleus of the nitrogen atom in your strand of DNA, whether it's this wheel going around, whether it's the second hand on the clock, moon going around the Earth, sun going around the Milky Way galaxy, doesn't make any difference. One revolution is 2 pi radians. Radius is not a factor. But how far it travels in that revolution in terms of linear distance is dependent upon that radius. Okay? Got that idea? Now, let's talk about the next one. And that's V equals R omega. Now, this one is pretty specific about the terminology, because sometimes you see this written different ways. And I'll give you some different examples. One's called, sometimes you'll see this called tangential velocity. Sometimes you'll see it called linear velocity, okay? But no matter what, this is always your angular velocity. So here's the visual on this one. So imagine here's this wheel. You don't have to imagine very much. Here's a wheel. Oh, that took a big leap of faith, Brooke. Okay. So imagine that you have a radar gun, Okay, so Leslie's over there, and she has a radar gun. I'm gonna put this rock up here. And this is gonna come around like this, and she's gonna shoot that radar gun, and she's gonna bounce that radar gun off of the edge of this rock. And so her radar gun only measures in meters per second. It doesn't measure in radians per second. So as this wheel comes around, she's gonna shoot that, and it might say like 5 meters per second, okay? So that 5 meters per second would be the same whether this is coming around like this or I just move that towards it, okay? That's gonna be 5 meters per second. So the other way that you can visualize this is that this wheel goes around, and you wanted to walk and just keep up with it. So that 5 meters per second would be how fast you would have to walk to keep up with that point on the wheel. Okay? Got that visual? Now, imagine this. I'm going to take that same rock, but I'm going to put it really close to the edge. So, would the radar gun read the same as it is on the outside as it does on the inside? Would the speed be the same? Would the measured speed be the same on the outside as it is on the inside? Morella, you shake your head no. Why?
Because it's measured in meters per second, not radians.
Yep.
So, your radius is smaller, so. Or no. Yeah. It's smaller.
So?
So then it's less distance for every revolution. Right?
Yes.
Yeah.
Yeah.
So I feel like I'm not getting where you want me to get.
You're about 90% of the way there.
Can you give me a little hint?
No, I'm going to completely leave you hanging. Okay? I want everybody in the room to be just as confused as you are.
So why wouldn't it be the same?
Okay,
I don't know,
so
because that's why.
Here's the deal. Imagine that you're in the marching band. Okay? All right. Anybody here was ever in the marching band? Okay. Let's hear it for the band members. Okay. All right. So here's the deal. Imagine that you're in a band and you're trying to do a formation where you walk around like this. Okay? And everybody's in the same line. Who has to walk faster? The person on the outside, the person on the inside, or is it the same?
The outside.
The outside. Now, do they all take the same amount of time to complete one revolution?
Yeah.
So time is the same, right? We've talked about this. Time is the same. But if you're on the outside, you have to travel a greater distance in the same amount of time, so you have to walk faster. Okay? Does that make sense?
Yes.
So when you look at this V equals R omega, so every point on this wheel is traveling at the same number of radians per second, okay? Because they're all taking the same amount of time to complete. So no matter what, every point on this wheel, whether it's right here by the spokes or way out here on the edge, everything is traveling in 2 pi radians at a certain amount of time, okay? But the measured velocity, what we call tangential velocity or linear velocity, changes depending upon where you are. So if you're out here, that radar gun is going to show a much bigger velocity than you do closer to the center. Okay? Now let me give you an example. Believe it or not, every time you have driven your car, you have used that equation. And you go, Burkamp, I've never seen this equation before in my life. I said, you have used this equation every time you've driven your car. I go, no. Yeah, let me show you. So a little lesson in auto mechanics. So here's your engine, okay, all right? And it transmits power out to your wheels, okay, all right? And so somewhere in there, that's hooked up to your speedometer, there's some device, it's mechanical, maybe it's an electronic sensor. What it's doing is that it's measuring a certain rate of spin, that something is spinning within your transmission. So basically what that's measuring is omega. Okay, it's measuring a certain rate of spin. Okay? Now, if you've never done this, if you open up your driver's side door, there should be, on the frame, there should be a sticker, and it's going to say the size of tires that your car is made for. So basically what happens is that when that car leaves the factory, the engineers have said V equals R omega. And it's gonna say, okay, so for a certain size tire, when your wheel is spinning at a certain rate, that's gonna be a certain linear velocity that your car is moving at. So if that thing is spinning at a certain number of radians per second based upon a certain size tire, your speedometer is gonna say you were going 40 miles per hour, okay? Now, but that's with a certain standard size tire from the factory. That's what those are different. Like typically it's like R15, radius 15 inches. But let's say that you're going through your rebel phase, okay? And you like to drive fast. Like they can't tell me how fast I'm driving. I want to stick it to the man. I'm a rebel, you idiot, you know. So, and you're getting all these speeding tickets. Your folks are about to kill you. Is this Sam?
Yes.
Oh, I have your solution, Sam. We're gonna use Sam then, okay? And Sam's like, I'm breaking the law, right? Bad boy,
I thought I was
right?
gonna cry today, you guys.
But his parents and his insurance company are about to kill him. But Sam wants to maintain this aura of being a bad boy, right? So he wants to think he's speeding, but he's really not. So imagine Sam takes off his normal sized tires and he puts on small little like lawnmower tires on his car. Okay? Now, so the omega is going to stay the same, but now he's going to shrink the radius of the tires. So what's that going to do to his linear velocity? It's going to become smaller, right? So Sam would be able to look at his speedometer and his little friends in the back going, look at Sam, he's a rebel, he's taking it to the man. He's driving 40 at a 30, he's cool, right? But in reality, Sam is only going like 30 miles an hour, okay? So he's gonna have the appearance of going fast, but in reality, he's not. Now, the other thing happens, and this is typically true of guys, and you don't see it as much anymore, but for a while, it was the cool thing to take a four-wheel drive pickup and take off the standard size tires and put on the big oversized tires, okay? Jack smiles. Okay,
Still a
right?
thing.
That's because like I'm cool, right? And so here's the problem. When you put on the big oversized tires, radius goes up, okay? So then what happens to your actual linear velocity? It increases. So you might think you're driving 40. Yeah, you're driving 45, 50, something like that. So then the cop pulls you over and goes, did you know you were speeding? No, sir, I thought I was driving 40. And they go, well, you have oversized tires. Didn't your physics teacher give you the lecture about V equals R omega? And if you say no, Burkamp never taught us that. I will go to court and testify against you. I will completely roll you under the bus and go, that is a bold-faced lie. And I said, I'll show him the YouTube video. Okay? This is when I taught Jack Ring this lesson. Okay? So, there you go. So if you ever put big oversized tires on your vehicle, just keep that in mind. Okay. Now, the same thing is true, oddly enough, when you get A equals or fish, right? Same idea. So A is your linear acceleration, alpha is your angular acceleration, okay? So you press down on the gas pedal. Fundamentally, what are you making your tires do? Yeah, you are making them undergo an acceleration, right? And so as that speeds up, guess what? Then that translates into a linear acceleration. You hit the brakes. Fundamentally, when you hit the brakes, you're trying to create a fish that makes you slow down, okay? That's it. So your gas pedal is basically, you're changing the size of your butt relative to the size of your fish. That's it, okay? Press down on the gas pedal, you want a bigger butt. Let off the gas pedal, you want a smaller butt. That's it, okay? It's all about the syncing, it's all about that. Okay, now, so here's the last big thing. And that's what's second to the last big thing. That a lot of these relationships, mathematical relationships, are the exact same. So just like you have V equals V naught, plus AT, you can write that as but equals but not plus fish time, okay? Just like if you draw a graph and it's velocity versus time, what does the slope of a velocity time graph give you?
Acceleration.
Acceleration. Oh, if you have positive acceleration with positive velocity, what are you doing? Speeding up, right? What does the area underneath the velocity time graph give you? Displacement. Guess what? If you were to draw a but time graph, what does the slope of that graph give you? Gives you acceleration. What do you think the area underneath that gives you? Displacement. Because this is going to be radians per second times seconds. Guess what? You get radians. If you have a horizontal line on that graph, what does that indicate?
No acceleration.
Yeah, your tires are spinning at a constant rate, okay? Same idea. So, V squared equals V naught squared plus 2AD. Guess what? That's but squared equals but naught squared plus 2 theta fish. So every relationship that exists for kinematic equations plays out the same way with angular motion. Basically, wherever there's a D, you put a theta. Wherever there's a fish, there's an A. Wherever there's a V, there's an angular velocity. Okay? That's it. Same idea. All right. Now, we have one last equation to talk about. And you have used this equation. What is it?
It's a cat.
A cat?
It's her cat.
It's a butt cat.
What's his name again? Something S.
I just randomly found it. I was showing Kaylee.
What's her name? What's his name? Scrappy.
You should give it to Mr. Fry.
Already did. There are two of
Oh
them
yeah,
now.
Kaylee. Hi, Kaylee. I forgot who we were sitting this to.
Shout out.
And Topher's in there. Hi,
Oh
Topher.
yeah, hi Topher.
Hi, Topher.
Topher's not watching that.
Oh, I promise you. I'll give you even odds on that. Okay. So torque, or if your French is torque, equals force times radius. And you go, Burkamp, I've never seen that equation before in my life. But yes, you have. You just don't know that you have. So here's the deal. Oddly enough, Wyatt, what do you think units force is measured in? Newtons.
You know what?
Radius is going to be measured in.
Meters.
So oddly enough, torque is measured in Newton meters. That's clever. Okay. Now, so let me give you an example. So
Nanometers.
So we'll start off, and we'll put the fulcrum
It is.
in the middle.
Happy
Okay.
Veterans Day.
So right now, I've got the fulcrum in the middle, and I've got a 200 gram mass out here, and I've got a 50 gram mass here. Fulcrum's in the middle, 50 gram mass over here, 200 gram mass over here. If I let go of it, what's going to happen?
That one's gonna fall.
Why? Gravity is stronger?
No.
Yeah, it is. Gravity's pulling down more on the
Yeah.
200. That's
That's what I meant, yeah.
They're equidistant apart, and
So
one
what?
has a bigger force, so of course it's gonna happen.
Of
course.
So force.
I learned about this in my 7th grade engineering class. I remember.
I've done this in engineering.
Hey, did we have class together?
We
Did
could have.
they make you go like this when you talk about torque?
Yeah, I think so.
Because both
Did
of
you have
were
that
gi-
really weird guy?
both of
Make
you
it
were
team?
giving me this kind of, okay, stop.
Sorry.
Okay. Feel like I'm being scolded. Okay, so here's the deal. Torque is a product of two things, force and, so the radius is the same.
Yes.
So this has more force, so that's going to create
More torque.
more torque. So when I let go of it, oddly enough, it goes on.
Oh wow.
Now, well, let's say we want to balance these,
Yeah.
okay? If I do want it to balance, what do I want to do?
Provide a bigger radius.
Increase radius to small force.
So I can't move this one, this is as far as out as it can go,
So move that
Yeah,
one
make the
to
radius,
smaller.
yeah.
okay?
This is quite interesting. Wow.
Ooh.
Huh?
That's Ooh.
Okay, solid,
Yes.
magic, sorcery,
Oh, my bad.
okay, witchcraft, even better, burning at the stake. All right, so here's the deal. So in this situation, the two torques are the same. So when you talk about torque, you talk about two types of torque. So when I look at it from your perspective, this side over here is what we call counterclockwise torque. Yes, this goes back to the old days when you had hands on a clock and not a digital, okay? So counterclockwise torque is coming around like this. So this counterclockwise torque here is equal to the clockwise torque going this way. So basically, this is balancing everything out, okay? Now, so whenever something balances, the two torques are the same. Now, your other option is that I move this back out here, but now I can adjust what we call the fulcrum. The fulcrum is the point where it balances, okay? So if I want this thing to balance, where do I want the fulcrum to be? Closer to the big mass, closer to the smaller one?
Close to
Big.
the mass.
Yeah, so if I move this over here, like this, and I get that to pretty much balance.
What do they use torque for?
So,
Like, yeah, that's what I remember. It was like something about a truck, but like,
Diesel
what's the point?
Diesel.
But why?
Towing.
you'll see. Okay, so, now here's the deal. Is it balanced?
Yes.
Yeah.
Two torques are the same.
Yes.
Small force,
Big
radius.
Radius.
big force.
Small
Radius.
Okay, now this is where I said you all have used this
Whoa.
equation every day. So give that a spin.
Which way? This way?
Okay. So the bell rings, and you want to leave the room, right? Do you have to apply torque to the door?
Yes.
Yeah.
Yes, because torque refers to things that spin about an axis. So you have one of two options. You can either push here on the edge of the door out here, or you could push right here by the hinges. Which one will require more torque? Outside, inside, or is the torque the same?
Torque is inside.
Torque's the same.
Torque
No.
is the
It's
same,
the same,
okay?
Why?
It's gonna take the same amount of torque to make this door open.
yeah. You know,
Okay.
less force on
So the torque is gonna be the same.
more force on
But by pushing
torque is
by
the
the
same.
hinges, why is that gonna be much more difficult?
Because you have to apply more force to get the same amount of torque.
Yeah, so the radius is really small. So to create
You
the
said it
same
weird.
amount of torque, I'd have to
just
push
like he did.
More.
really hard. So I can do this,
Big force, small radius.
but
Super.
you have to push really, really hard, okay? Now, out here, I've greatly increased the radius. I can just go like this. So this is why, often enough, we put the handles over here and not right here, okay? You can put them here, but this is, okay? That's a long way from the frame over there. So, the same thing is true when you look at the cabinets in your house. So there's your cabinets. Where do you put the handles?
The
The
inside.
middle.
The inside.
Oh.
Away from the
You
hinges.
put them here, right?
The middle, yes.
Anything magic about that?
Yep.
What's the magic?
There's no
You
magic.
could put the hinges here, or you could put the doors handles here.
Well, that's not very fun.
But
You have to like pull
It'd be
it.
harder to-
yeah, it'd just be harder to open.
Or you just rip off.
That's an awkward
Rip
moment.
them off.
Yeah.
So technically, if we did this, we could make everybody way more strong. It's true.
Yeah.
The world would be stronger.
The world would be stronger
The world would be
because of
stronger.
physics.
Sam is thinking of like Sam to the same.
Now, look at your car door. Where are your handles on your car door? Same thing, okay? So, if you ever, let's say for example, you have a flat tire.
Alan knows all about that.
okay?
Filled out.
There's your flat
Oh.
tire, right? And you need to loosen the lug nuts. And you're pushing, you got the wrench and you're pushing on it and you can't get it loose. What do?
Apply more force.
Yeah. No.
You hold the
You're
wrench on.
push as hard as you can.
You hold the wrench all the way at the end.
Increase the
Number one.
radius.
Or you take a piece of pipe and you put that on the end of it. So then, when you apply that same amount of force, you've created more torque. Okay? So if you ever have to do something like that, I gotta change, I can't get them loose. Oh, working camp talked about torque. Oh, find a piece of pipe, put that on there. Okay, got it? Good? Rand? Stop that.
Just be strong enough though.
Okay, so let's make sure everybody's cool with how I want this thing started. So I want to calculate the angular velocity, and I even tell you in radians per second for the hour, minute, and second hands on a clock. Okay? So here's the clock. You got 3 hands. Right now, the hour hand is pointing at 1, the minute hand is pointing at about 1:15, and then you've got the second hand. So let's start with the hour hand. So the hour hand is going to go all the way around like this, right? How many radians is it going to move through?
2 pi.
2 pi. How long now? So we're going to use,
30.
we're trying to find omega, so that's going to be theta divided by time.
Oh, jeez.
So that's going to travel through 2 pi radians. Now, how long is that going to take for that hour hand to get back to that point?
3,600
3,600 what?
seconds. Right? Or,
Which would be 1 hour?
yeah, but you
So
want
the
it in
hour hand
rads
takes
per
1 hour to
second.
go all the way around. Makes sense, we call it the hour hand.
Yes.
Everybody solid with that?
Yeah.
Wait, no. It takes 12
Don't be.
hours.
Oh
No, it's 12 hours. That's not my fault.
That's the minute hand.
Okay. Right now it's pointing to the 1. How long is it going to take for it to get
That's my
back
bad.
and point to the 1? 12 hours. Okay? Yeah, little? And you were so confident in that hour, in that answer. Now, what are you going to have to do with the 12 hours? Now,
There you go.
1 hour, Marilla, is?
3,600 seconds.
There you go. Okay, I was gonna use that number just because waiting for it. Okay, now, so I want to make sure everybody has this answer. So somebody take 2 pi, divide that by the quantity 12 times 3,600. I want 3 significant digits and scientific notation.
1.45 e to the negative.
What'd you get?
1.45 e to the negative 4.
Times 10 to the negative 4th. Now, what units?
Radians per sec.
Radians per second. Okay, that's cool. Lovely. Now, so that's for the hour hand. Now, let's talk about the minute hand.
Yeah.
Let's talk about that, shall we? So, gravity storm.
Wait, how many?
So, how long is it going to take for the minute hand to make 1 revolution?
60 minutes.
Yeah.
That's going to be 60 minutes.
3,600 seconds.
No.
No, you just
She's
told.
right.
Oh yeah.
Yeah, it's 1 hour. Isn't it?
But it's, you would multiply that by the minute.
Am I being really stupid right now?
No, you're
No, you're being fine.
Right.
It's 30 seconds an hour, yeah.
Oh.
Okay, so for the hour hand, right?
My gosh, that would have been super amazing.
You never do anything right.
That's going to take 1 hour, and 1 hour is
Is it for the?
3,600 seconds. This is for the minute hand.
Yeah, okay.
This is for the minute hand.
This is why we wear it.
This is why you have digital watches. Now, what about for the second hand?
60.
60 seconds. So which one of those 3 is traveling at the greatest angular velocity, the second hand, the minute hand, or the hour hand?
Second.
Second hand, because that takes the least amount of time to make one revolution. Now, I want you to look, I want you to focus on something right quick. Did I give you the radius of those hands?
No,
No. Why?
because it doesn't matter
Doesn't matter.
for
So,
angular.
that's true whether it's the watch here, whether it's that, whether it's Big Ben in downtown London, okay? So what I want you to see is that the radius in this calculation is not a factor, okay? Now, when you get to number 2, I tell you the tip of the second hand of the watch is 14 millimeters from the axis. What's the linear velocity? So linear or tangential velocity, this is where you're going to use V equals R omega. You already have the omega, okay? We calculated that up above, okay? You just have to deal with that radius. So you have to pay attention whether you're talking about tangential or linear velocity versus angular velocity. Angular velocity is not dependent upon the radius, but your linear or tangential velocity is. Now, when you get to number 10, okay, let me paint the picture on what's happening on number 10. Here's this teeter-totter, and it's 1.75 meters long. And you've got George on one end, and you have Joe on the other. And George has a mass of 56 kilograms, and Joe has a mass of 43 kilograms. Now, what you're trying to do is figure out where to put the fulcrum so that everything balances out, okay? So think this through. Is the fulcrum going to be closer to George or closer to Joe?
George.
Why?
George has more mass.
He has more mass. There's going to be more force over there, right? So you put the fulcrum somewhere in here. So here's what you want to think of. The torque from George has to equal the torque from Joe. True?
See,
Cool with that. Now, what 2 things do you have to do to calculate the torque for George? What 2 things do you need? The force from George times some radius, that has to equal the force from Joe times her radius, right? Now, the problem is the radius. Sketchy, okay? So one thing you can do is guess and check. You could let this be 0.25. So if this is 0.25 and the total length is 1.75, what's the distance to Joe? 1.5, right? What's left over. And you can do that. You can just keep going back and forth until you get them to balance. It works. It's a god-awful long process, but it works, okay? Or you can let algebra come to the rescue. So what do you want the distance to George be? How about x? Okay, now this is where it's not gonna be near as complicated, but this is gonna be like the Lagrange point calculations that you did to the moon. So if the distance to George is x, what's the distance to Joe? 1.75 minus x. So if this is gonna be x, this distance here is gonna be 7.5 minus x, okay? So then you're gonna distribute this, get all your x's on one side, get all the numbers on the other. It turns into an algebra problem at that point. When you get to the back side, on question 17, you need to draw a graph of angular velocity versus time. This is just a sketch, okay? This is just a sketch. Keep that in mind. Try not to math nerd too much and leave these in terms of radians, okay? If you're really hardcore, you can. I prefer that they be in decimals just because that's what you're physically going to measure. All right, my voice is about to die. We're done.
You should get some cup jocks.